All right, get that going. Want the blue. Been a little bit since our last meeting, so let's do a quick recap. First off, using high-level language, what's a topology? Go ahead.
The minimum structure required to preserve proximity in sets.
To talk about proximity on the set, when we use a continuous function, that preserves proximity. So first you have to give it the structure before we preserve the structure. So functions preserve structure, but yes, topology is structure we give a set. Remember, when we think about R2, most times when we talk about R2, we think about the plane. But when we think about R2 as a set, we shouldn't think about it as a plane. You shouldn't think about it as this whiteboard. You should think, I take this whiteboard and I run it through some shredder that shreds up into really, really fine dust, powder. Take that dust, put it in a bucket, shake it around. There's R2. All the points right there are right there in the bucket. No structure. Topology is a structure we impose upon that set, which then enables us to talk about points in some sense being close to each other, being next to each other. Or, as he said, talk about proximity. Now, we got the notion of a homeomorphism. A homeomorphism, well, a little bit more terminology. So when we take a set and we give it a topology, so it has that structure, what do we call the whole resulting structure? I take a set and I give it a topology. And I have what we call a topological space. So it's very common in mathematics that when you take some set and you give it some structure, your result is some sort of space. Up till now, we've pretty much been talking about topological spaces. Now we have the notion of a homeomorphism. What is a homeomorphism?
It's been a while, but two topologies are homeomorphic if you can find a bijection from one to the other that preserves proximity.
That preserves proximity both ways. Perfect. Slightly different way of saying the exact same thing. A homeomorphism is a function from one topological space to another that's a bijection, and it's continuous, and its inverse is continuous. So he says it preserves proximity. That's what we mean by continuous function. A continuous function is a function that preserves proximity. So perfect. All right, so last section was a lot of just feel-good examples with homeomorphisms and getting a sense for one's topological space being homeomorphic or somehow the same as some other topological space. And we did a bunch of feel-good examples, not very rigorous, just to help develop your intuition. So we're just finishing off the end of that. So we just had a couple definitions here and then one more theorem, and then we're on to a completely different subject. So our first definition here is the definition of what it means to be an embedding. So a function f from x to y, x and y are going to be topological spaces. Not sure I said that. So x and y are topological spaces that have their own topologies. So a function f from x to y is called an embedding, provided that it maps x homeomorphically to f of x, where f of x is a subspace of y. So x, here's the entire topological space x. It's the orange points. This is not a point in x. This is. Y is this rectangle. This is a point in y. This is a point in y. This is also a point in y. So f maps x to, here's f of x, that weird shape there. And intuitively, you can see from the picture, oh yeah, those are homeomorphic to each other. Those are topologically the same. We can find a mapping that anytime the points are close over here, they're close over here. And anytime they're close over here, they're close over here. So there we go. So this is an embedding of this. So we call the function f the embedding. F embeds x in y. And here's how it maps it. Make sense? Pretty straightforward definition. Hopefully the picture helps a lot. Okay, so now we're going to talk about two special types of embeddings. A path, and then a simple closed curve. So the image of f maps from -1 to 1 to x. So let me mess with my picture here. So this time we're mapping, remember -1 to 1, we think about that as a closed interval on the real number line. So it's going from -1 to 1. And it's just these points including its endpoints. And we're mapping that in here. If we map that in here homeomorphically, what is it going to look like? It's going to look something like this, right? If I take that and I embed it in there, so that's what we're going to be talking about. So the image of this thing, the image is the one over here. This is the pre-image, this is the image. The image of this function is called an arc or a path in x. So now, this is what we're calling x over here, because this was just -1 to 1, here's x. So this image is called an arc or a path in x, and the image of g, well, we'll skip over g for a second. So the image of that is an arc or a path in x, provided that f is an embedding. So as long as f is doing this homeomorphically, then the image is called an arc or a path. Now imagine that instead of mapping in -1 to 1, I mapped in S1, which is a circle. Remember, we're not including the interior, we're not including the exterior. A circle just means those boundary points. What would that look like if we mapped it homeomorphically into here? It would look some shape like this, right? Something like that. And so this, we then call, the image of this, we call a simple closed curve. And this was the example of G. So G now is mapping S1 to X. We call it a simple closed curve in X, provided that G is an embedding. So two special types of embeddings. We talked about an embedding, which gives us an arc or a path, and then embedding, which gives us a simply closed curve. I can't remember if it was someone in here, we started talking a little bit about knot theory. Any of you?
I know about it. Was that?
So the definition of a knot is an embedding of S1 in this R3 space. That's what a knot is. It's an embedding of S1 in this space. So that's the definition of a knot. I don't know if we'll ever do anything with knots in this class, but
Like a K-N-O-T?
yes,
Okay.
the knottiest version of knot theory. All right. So talked about arc, talked about path, and talked about simply closed curve. All right, I think we're good there. And then the last thing we were going to prove, remember that we use this congruent symbol in this class to say homeomorphic. So if x is homeomorphic to y, so it's understood x and y are topological spaces, they have their own associated topologies. If x is homeomorphic to y, and x is Hausdorff, so is y. Remember what it means for a topological space to be Hausdorff. Go ahead.
It means that for every point you can find a neighborhood around it that doesn't intersect. So a point x and y, you can find a neighborhood around x that does not intersect with the neighborhood around y.
Perfect. A topological space is Hausdorff if for any 2 points I choose, I can find neighborhoods for those points that don't overlap. I can house those points off from each other. That's the mnemonic device we remember for Hausdorff. I can house off the points from each other, give them their own neighborhoods. So I told you when we first talked about Hausdorff that this is the first topological property we have. This is the first property that we can say a topology either has that property or does not have that property. It's hard to come up with these properties that topologies can and cannot have. Here's one of them, Hausdorff. So if a homeomorphism preserves all topological structure, and one of them is Hausdorff, the other one better be Hausdorff. To give you a geometry analogy, if two triangles have the same geometric structure, if they're congruent, and one of them's a right triangle, the other one has to be a right triangle. Because that's a property, a geometric figure, a triangle could have. So Hausdorff is a property a topological space can have. And so any topological, if we're saying two things are topologically equivalent, what that means is all topological properties they have in common. Well, that's not quite what it means, but it's good intuition. Okay, so we're going to prove that this is the case. Not a lot of space here. I'll just kind of finish over here if I need to. Okay, so 1. Let x be homeomorphic to y, where x is Hausdorff. Now I'm trying to prove that y is Hausdorff. Right? So how do I prove y is Hausdorff? I need to grab two arbitrary points out of y and show that they have their own neighborhoods that don't overlap. So 2. Let f sub x and f sub y be any 2 points in y where x and y are obviously the points in x that map to them. So we're going to grab two random points in y, and since f, oh, I didn't say f is their homeomorphism. So sorry. Let f be the homeomorphism from x to y. Let's justify that statement for a second. If x is homeomorphic to y, what does that mean by definition? It means that there exists a homeomorphism that maps x to y. So, if x is homeomorphic to y, there must exist some function f that I know is 1-to-1, or sorry, that I know is a bijection, so 1-to-1 and onto, continuous, and its preimage is continuous. Not its preimage, its inverse, sorry.
Oh, yeah.
The inverse of the function. Preimage is talking about that. Okay. Notice that if x is homeomorphic to y, there could be tens of thousands, millions, even infinite functions that do this. All I'm guaranteed is there's at least one function f. That's a homeomorphism from x to y. I know nothing about that f, except for that's a bijection, it's continuous, and its inverse is continuous. That's all we know. And so that's the only facts I can use to try and prove that y is also Hausdorff. Okay, so now let's grab 2 points in y. 3. So let f of x and f of y in y where x, y in x with x not equal to y. So they're two distinct points. So how do I know if I grab 2 points in y that I can find 2 points in x that map to them? Because f is a bijection, and so it's on 2. And so it definitely maps to all of y. So any two things in y were definitely mapped to from something in x. And if f of x is not equal to f of y, then x can't be equal to y. Because otherwise the function wouldn't be on 2, or sorry, wouldn't be 1-to-1. So I get that from the fact that f is a bijection. That's why B is so far. Okay. 4. Now what am I trying to do? I'm trying to find a neighborhood of f of x and a neighborhood of f of y such that they have no overlap. Their intersection is empty. Okay. Now, since x is Hausdorff, comma, there exists u sub 1 and u sub 2 open in x such that x is in u sub 1, comma, y is in u sub 2, comma, and u sub 1 intersect u sub 2 is equal to the empty set. Right? We get that from the fact that x is Hausdorff. Now we're going to look at their images. So we're at 5. Let v1 be the image of u1. v2 be the image of u2. And observe that, what do I know about v1 and v2? So v1 is the image of u1, v2 is the image of u2. We know that. What else do we know?
We know they have to have all the points in U1 and U2.
Yeah, all the points in u1 have to map to v1, and all the points in u2 have to map to v2.
And we know that they don't. We know that V1 and V2 do not intersect.
And we know that v1 intersect v2
Is the empty set.
is equal to the empty set. How do we know that?
Because their preimage, their intersection of their preimages was equal to the empty set.
Yeah, if their preimages have nothing in common, and the function's a bijection, then their images can have nothing in common. U1 here might be the numbers 1, 2, 3. U2 here might be the numbers 4, 5, 6. They have nothing in common. When we map them, whatever 1, 2, and 3 maps to has to be completely different from what 4, 5, and 6 maps to. Otherwise, our function wasn't a bijection. It's not mapping each element to one and only one other element. So that's how we know that those two have an empty intersection. Perfect. All right, so I found two sets over here. They contain, so observe that their intersection is empty, and maybe this is trivial, but just state it. And f sub x is in v1, comma, f sub x is in v1, I'll just say and again, although it sounds bad. And f of y is in v2. Okay, so I found a set containing f of x and a set containing f of y such that their intersection is empty. But we're not done yet. I need to prove that v1 and v2 are open. How do I argue that they're open? So far I've just used the fact that f is a bijection. I have not yet used the fact that f is in fact a homeomorphism. So how am I going to argue that v1 and v2 are open?
Because they were open in their preimage.
Their preimage is open. What's the definition of a continuous function?
The preimage of open sets are open.
The preimage of open sets are open. So if these were open, we know those are open.
Yes.
So that doesn't help us. But since this is a homeomorphism, its inverse is also continuous. Or in other words, the image of open sets are open under a homeomorphism. So these are open. So 6. Since f is a homeomorphism, comma, v1 and v2 are open. And we're done. We just barely found two open sets, namely v1 and v2, whose intersection is empty, and where v1 contains our first point and v2 contains our second point. So I grabbed two arbitrary points. I was able to find two open sets around them that have no overlap. So we just barely proved that if two topological spaces are homeomorphic, and one of them is Hausdorff, the other one has to be Hausdorff, which is very much what we expected. All right, any other questions on that or homeomorphisms in general before we completely switch gears?
I understand the definition of the Hausdorff, but I can't remember. Did we do an example of Hausdorff?
The easiest example is R2. So imagine we're in R2 with the standard topology. So our open sets are created from open balls and unions of open balls. Pick any two random points in R2 you want. Doesn't matter how close together you drew them. So I'm going to pick these 2 points, really close to each other. I'm going to redraw them scaled differently right here. So this is just a redrawing of those 2 points, rescale.
Zoomed in.
Zoomed in. No matter how close you make them, I can always create open balls small enough around them such that those open balls have no overlap.
Well, couldn't you say that's the case for every single point in the topological space? Because
Not for every single point in a topological space. No.
give me an example of that.
So they're just not going to be very intuitive ones. Remember when we first came across this Hausdorff, it was first thought that this needs to be a property of topologies. And then we realized actually this doesn't need to be a property of topologies, and there's really weird topologies out there. So going back, the really weird one we already talked about is the finite complement topology. Your sets are open if they have a finite complement. So we're talking about on R. So what is an open set? Open sets look like R minus some finite number of points. 1, 2, 3. Here's one possible open set.
Okay.
Take that, remove those points. It's now a set whose complement is finite. Because what's its complement? The set 1, 2, 3. It's everything but those points. Pick any two open sets you want. So here's one potential open set. Another open set has to be of the form R minus a finite number of points. In this case, we might get rid of pi e, the square root of 2, and 97. These two open sets are always going to have points in common. You can't pick two open sets other than all of R in the empty set. You can't find two open sets that don't have some overlap.
Overlap meaning that
There's a point that's going to be in both of these.
Yeah, okay, so that's what you mean by overlap.
Overlap, yes. point in common. If you were to take this set and you were to take this set and intersect them, the resulting set would have members in it.
Right. So okay. So a Hausdorff is basically that there are no points.
Hausdorff is pick any 2 points you want. I can always find open sets containing those points that don't overlap.
Okay. Well,
If we use a finite complement topology, and the two numbers I pick are pi and 2. Notice that this contains pi, and notice that this contains 2.
yes.
Yes, this is all of R
Okay.
except the numbers 1, 2, and 3. This is all of R except for pi, e, root 2, and 97.
Okay.
So 2's in here, pi's in here.
Yeah.
So here's an open set containing pi, here's an open set containing 2. Two random points in R. They're going to have an overlap.
They are going to have overlap.
Yeah. Their overlap is infinite. Pick any random number you want. 0 is in both of them. 0.21 repeating forever is in both of them.
Okay. I get that because okay.
So it's only in these unintuitive topologies that you get that they're not Hausdorff. The ones that play nice and the ones that appeal to our intuition are always going to have this Hausdorff property, which is why it was almost included in the definition of a topology.
Oh. Okay.
So they're not going to be very intuitive ones. They're going to be ones that, to our intuition, it's going to be like, that's a useless topology. But nonetheless, it's out there.
I just kind of want to create some clear boundaries around these circles we've drawn. It kind of gives me a sense that there's it has something to do with space and distance, which I know is not a factor in topological space.
We're about to get to that. So we're going to get to metric spaces. We're going to show how we can create topologies for metric spaces where we have distances. And it turns out that those are always going to be Hausdorff. So when you have distances, when you include distances, we're going to see that that always gives you the Hausdorff property. So there is a close relationship there between distances and Hausdorff.
Okay.
But it's not necessarily there. Another simple example would be, imagine I take the topology 1, 2, 3. Oops. So here's my set 1, 2, 3. And what's the topology I give it? I'm going to do the power set of that. The power set of this. Now it's Hausdorff. Pick any two things out of there, 1 and 2. Can I find an open set containing that and an open set containing that don't overlap? Yeah, the set containing 1 and the set containing 2. So we can still get Hausdorff in situations where distance makes 0 sense. But you're still going to see from this next section how Hausdorff is closely related to distances. So there is some good intuition to be had there. Okay. Any other questions with the homeomorphism stuff? No? All right, then here's this right here. So I don't think it's anything. And now we're going to completely shift gears now to talking about metrics and metric spaces. So it's kind of like we're pushing reset on the class for a second. So now we're going to take some set, and we're going to give it some structure. And the structure that we're going to give it is called a metric. So before we took a set and we gave it a topology, that was some structure. And the topology gave us a notion of proximity. Now we're going to take a set, and we're going to give it some structure called a metric. And a metric intuitively gives us a notion of distance. It's going to give us a way of determining the distance between any 2 points. A topology was just able to tell us if points were close to each other or not. A metric is able to tell us exactly how close they are between any 2 points. It doesn't just answer yes or no, these points are close. It says, not only can I tell you which points are close, I can tell you exactly how close they are, exactly how far they are. So a metric, intuitively, is going to give us a lot more structure than just a topology. A topology just says they're close, yes or no. A metric says, not only can I tell you which ones are close, I can tell you exactly how close everything is. Pick any 2 points you want. I can tell you how close they are. All a topology can say is, I give you these 2 points. Are they close? No. That's it. So intuitively, a metric is going to give us a lot more structure than a topology. A metric space has a lot more structure than a topological space. Okay, so let's get into exactly what a metric is now. So a metric on X is a function, D, which takes two elements of x and spits out a real number r. It takes two elements of x and it spits out the distance between them. You give it 2 points and it says they're this far away. Okay, so a metric on x is a function, d, from x cross x to r, such that these three properties hold. Property number 1, for any 2 points, their distance has to be greater than or equal to 0. Negative distance doesn't make sense. And their distance can equal 0 if and only if x and y happen to be the same point. So if I pick 2 points that aren't the same point, then their distance cannot be 0. If I try to find the distance between this point and itself, its distance is always and forever 0. That's the first property that a metric has. Good so far? Second one, pretty intuitive. For any x and y, the distance between x and y is equal to the distance between y and x. Or in other words, metrics are, what's that property in general? If the distance from x to y is equal to the distance from y to x, then we say that metrics are not congruent. What? Not bijection. This is getting back to our properties that relations can have. And equivalence relations have these three properties. We said they're symmetric.
Symmetric. Okay.
Symmetric. So the distance function is symmetric. The distance from x to y is equal to the distance from y to x. It's symmetric. Okay, and then the third one, not transitive. The third one is for any 3 points x, y, and z, the distance from x to y plus the distance from y to z has to always be greater than or equal to the distance from x to z. We call this a triangle inequality. And then we call x together with d a metric space. So x is our set, d is our metric, xd, metric space. Just like we have topological space, now we have a metric space. Now, let's come back to this triangle inequality for a second and explain it a little bit to help you understand its name. So, we're going to draw a triangle. We're going to use just R2 with the Euclidean metric to help get some intuition here. What is it saying? If this is a point x, this is a point y, and this is a point z, it's saying the distance from x to y plus the distance from y to z always has to be greater than or equal to the distance from x to z.
Why is that the case?
Well, it's a property that a function has to have if it's going to be a metric. If your function doesn't have this property, fine, it's not a metric. What is it? I don't know. But if you choose a function so that it satisfies these three properties, then your function is a metric. And so we're going to prove that functions that are metrics, you get all this other stuff for free from it. So if we use, surprise, surprise, the way that we calculate distances using the Euclidean metric, the way you're used to calculating distances, is in fact a metric. And so if you think about using distances the way you know and love, the distance from here to here plus the distance from here to here is always greater than or equal to the distance from here to here. It's one of the things you prove in geometry.
It almost seems like you wouldn't even need to have that as a property, but what do I know?
Well, we'll see some different metrics rather than the straightforward Euclidean metric. The Euclidean metric's the nicest one. We're going to start calling that the standard metric, but there's lots of metrics. But anyway, so that's the triangle inequality. And that's where it gets its name, because this is the first context under which it was proved in Euclid's Elements. Okay, so we're going to do a deep dive into just one metric to get you a feel for these things, and then we'll introduce some other metrics and some feel-good examples. So the first metric that we're going to do a deep dive into is this metric right here. Let D be a function from R cross R to R. It's going to take two real numbers, and it's going to spit out the distance between them. Question, if D is from R cross R to R, what is the space we're defining a metric on? What is the set we're defining a metric on?
The real number plane.
The real number line, not the real number plane. Right? R. Notice that up here, when we were defining a metric on X, it was of the form D is from X cross X to R. This is what it is in general. We're doing a concrete metric now. It takes two real numbers, 2 points on the real number line, and spits out the distance between them. Here's how it's going to do it. It's going to do it in the most intuitive way. We're going to say that the distance between x and y is equal to the absolute value of their difference. It's exactly how you already know how to calculate the distance between 2 points. If I were to ask you, what's the distance between -8 and -3? It's 5. How do you calculate that? You can do the absolute value of -8 minus -3, or you could have done the absolute value of -3 minus -8. -8 minus -3 is the same thing as -8 plus 3 is the absolute value of -5. What's the absolute value of -5? 5. Similarly, -3 minus -8 is -3 plus 8 is equal to the absolute value of 5, which is equal to 5. Gives you the same thing both ways. So, pretty intuitive metric for how we're going to define distances on the real number line. So first, I'm going to prove that this is in fact a metric. That's what this example is working through. Okay? So before we do that, first let's get a rigorous definition. Goes a little bit outside the scope of this class. This is something that you typically come across in like a college algebra course. But what's the exact definition of absolute value of x? The absolute value of x is just x itself if x is greater than or equal to 0. It's negative x if x is less than 0. So strictly speaking, the absolute value of -3 is, let's check. So we're plugging -3 into here. Is -3 greater than or equal to 0? No. Is -3 less than 0? So the answer is it's negative whatever my x was. Or in other words, it's negative -3. And it happens to be the case that negative -3 is equal to 3. So the absolute value of -3, negative -3. All right, question to make sure you're paying attention. If a is less than 0, comma, then the absolute value of -a is equal to what? Negative a. Right? Which is just the same thing as a. So it's just a here, right? After we simplify? No! It's negative a. People working with absolute values get way too comfortable just throwing away negative signs and thinking that magically does it. Let's go back and think carefully through the definition. First off, I said if a is less than 0, let's think about that for a second. If a is less than 0, then negative a is greater than 0. So a less than 0 means negative a is greater than 0. Right? So I plug in negative a into the absolute value function. Is negative a greater than or equal to 0? Yeah, it's greater than 0. So it's greater than or equal to 0. So the absolute value of negative a is just a. Or it's just negative a. It just spits out whatever you put in.
Why?
So a, for example, could be the number -3. What's the absolute value of -3? It's negative 3. A is any number less than 0.
Yes.
So it could be -3.
Okay, right.
So then what's the absolute value of negative 3?
Positive value is 3.
It's negative 3 or positive 3.
Yes. Which would just make it 3 eventually.
Which would just make it 3, but how do I write that? I can't just say so it's equal to a because a is -3. I can't say it's equal to a because a was -3. It's equal to negative a or positive 3.
But the absolute value of negative a can't be negative a. Equal to
It is. So you get too comfortable from your basic algebra classes just throwing away negative signs because there's an absolute value there.
Okay, so if it's negative a, then you're basically saying whether there's an absolute there or not.
It depends on what a is. In this case, a was less than 0.
Okay.
So negative a is greater than 0.
Can you simplify it internally before you use the absolute operation?
It happens to be the case that negative a, the absolute value of negative a is also equal to the absolute value of a. Okay, but what's that equal to? It's equal to negative a.
See, the absolute value of a is not equal to negative a.
Yes, it is. Let's check.
Oh, shoot.
Let's check. Going through the definition. Remember, a is less than 0. So let's plug in. We're plugging in a. We spit out a if a is greater than or equal to 0. Is a greater than or equal to 0? No. So we spit out negative a. So this is the definition of absolute value.
Okay.
This is so weird.
Occasionally you have a textbook that says it's the number's distance from 0. That's backward thinking. We use absolute value to define distance. We don't use distance to define absolute value, as we're doing right here. So you have to be a little careful working with these absolute value things. It's real easy to make a mistake and to not think carefully about what the definition actually gives you. All right. So I'm trying to prove that D equal to this metric D is in fact a metric. I'm trying to prove it's a metric. So I need to show it has these three properties. Okay? Before I show it has these three properties, I'm going to just quickly walk through two little lemmas about the absolute value. A lemma is like a quick proof you do before your main proof. So there's just something that's going to be useful. So our first lemma is that x is always less than or equal to the absolute value of x. So let's really quick handle that. So if x is greater than or equal to 0, then the absolute value of x is just equal to x. So in that case, they're equal. If x is less than 0, sorry, that was it then. If x is less than 0, then the absolute value of x is equal to negative x is greater than 0. Right? But if x is less than 0, that means 0 is greater than x. So I show the absolute value of x is equal to this is greater than x. So the absolute value of x is greater than x, or the absolute value of x is equal to x. In either case, the absolute value of x is greater than or equal to x. You with me? Okay. Maybe I won't walk through the proof of this one. Pretty much the same thing. Just plug in the case where x is greater than or equal to 0, and then plug in the case where x is less than 0. See that in both cases it spits out the same thing. So won't bother with that. But these are two lemmas we're going to use now to show that this is a metric. Okay. Probably just do, well, I don't know. We can talk through this. So first, we need to show that this function d has this property. So is it the case that the absolute value of x is always greater than or equal to 0? Yes, the absolute value function is always greater than or equal to 0. How do we know that? Anytime we plug in a number greater than or equal to 0, it spits out a number greater than or equal to 0. Anytime we plug in a number less than 0, it spits out a number negative x greater than 0. So the absolute value function always spits out numbers greater than or equal to 0. Right?
Come on, if you put 0 in there.
Huh?
If you put 0 in there, wouldn't it be 0?
Yeah, it can spit out 0, but it always spits out numbers greater than or equal to 0.
Oh, greater than or equal to. Or greater
So
than.
this right here, remember this is our metric. Whatever that is, that's the absolute value of a number. It always has to be greater than or equal to 0. Now going back to your algebra days, if I know that the absolute value of x minus y is equal to 0, then the absolute value of x minus y is either equal to the positive of that or the negative of that. You're not used to that algebra? If I told you that the absolute value of x minus y is equal to 7, then that means x minus y is either equal to 7 or x minus y is equal to negative 7.
Yeah, so,
Right? So if I tell you it's equal to 0, then that means it's either equal to positive 0 or it's equal to negative 0. Now, it turns out that 0 and negative 0 are the same. We proved that in a real analysis course. That's not this course. So we'll take that for granted. So the absolute value of x minus y equals 0 if and only if x minus y equals 0, which is the same thing as transpose the y onto the other side, x equals y. So the absolute value function is always greater than or equal to 0, and this will only spit out exactly 0. It spits out exactly 0 if and only if x is equal to y. So that satisfies the first property. The second property we get from this lemma. So I need to show you it's symmetric. I need to show you that the absolute value of x minus y is equal to the absolute value of y minus x. That's what I need to show you. You ready? So x minus y, using this lemma, if we multiply by negative, it doesn't change anything, is equal to negative x minus y. Right? I just took the inside and prepended a negative. Okay, now distribute the negative through. This is equal to the absolute value of negative x plus y. And now, addition is commutative. So I can change the order.
Okay.
So this is the same thing as y plus negative x, or the same thing as y minus x. Okay, so it's symmetric. The absolute value of x minus y is equal to the absolute value of y minus x. Okay, finally, we need to prove the triangle inequality. What does the triangle inequality look like for this? Here's the only one I'll actually bother writing out the proof, since it takes more than just one line. The triangle inequality, we need to prove. I'm going to prove the triangle inequality in a slightly more general sense and then come back to this. So, the triangle inequality is that I need to prove that the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Seems unrelated. We'll see how it's related to this here in a second. This is really saying the same thing as this. I know it doesn't seem like it at first glance. At first blush, we'll show you how. But first, let me prove this. So if you were taking algebra course or a real analysis course and you talked about the triangle inequality, this is what they'd be talking about. So it's worth proving because it comes up in separate contexts beyond this course. You've likely already heard or seen references before. So here's what we're going to prove. Turns out it's the same thing as proving this for this metric. Okay, so prove that this is the case. We're going to handle, well, how do I want to say this? So, observe that how do I want to do this? I should have thought about this for a second before. The absolute value of x plus y I don't want to sandwich that. Is there a way to do this without sandwiching it? Value of x plus y. Say it that way. I had an idea from the well, maybe I'll just grab by the horns and figure it out as we go. So, trying to think about the two cases to break this up into. Think about the case where x plus y is greater than or equal to 0, and think about the case where x plus y is less than 0, and see if that works out for us. So, observe that if x plus y is greater than or equal to 0, comma, then the absolute value of x plus y is equal to what? If the inside is greater than or equal to 0, the absolute value of the function is
Greater than
what is it? So I know that x plus y is a number greater than or equal to 0. So if I plug that into the absolute value function, what do I get?
Same number.
I just get out the same thing I plugged in. So this would just be equal to x plus y, right? And now what do I know? I know that x is always less than or equal to its absolute value, and y is always less than or equal to its absolute value. So this is going to be less than or equal to the absolute value of x plus the absolute value of y. So that's one case. Now I'm going to handle the other case. Everyone see how that case makes sense? Okay. 2. Observe that if x plus y is less than 0, comma, then, now what does the absolute value of x plus y equal?
Negative x plus y.
It equals negative x plus y, right? You with me? Distribute through the negative, that's the same thing as negative x plus negative y. Maybe put them both in parentheses like that, right? You with me? Now we're using our lemma that a number is always less than or equal to its absolute value. So this is less than or equal to the absolute value of negative x. This is less than or equal to the absolute value of negative y. You with me? Now we use a second lemma. We can get rid of the negative sign inside of an absolute value and it doesn't change anything. So this is equal to the absolute value of x plus the absolute value of y. Okay, yeah. Should just start doing it rather than trying to think ahead. So there we go. We proved that the absolute value of x plus y is always less than or equal to the absolute value of x plus the absolute value of y. Now I told you that this is going to give us this for free when we're talking about our metric. So now let's see that for our metric. So now I need to pick any 3 numbers, x, y, and z, and make sure this holds. You with me? So now, kind of aside from that proof, so pick any 3 numbers, x, y, and z. We're trying to show that the distance from x to y, let's try it this way. The distance from x to z is less than or equal to the distance from x to y plus the distance from y to z, right? Just flipping the order I write. So I'm rewriting this right here. So x, y, and z are any 3 real numbers. I need to show that this is always the case. When we're using our metric here, or when d is defined to be the absolute value. So this is the same thing as the absolute value of x minus z. We're trying to show that this is less than or equal to the absolute value of x minus y plus the absolute value of y minus z. So I need to prove that this is the case. Now I'm just going to rewrite this side kind of funny. I'm going to rewrite that as x minus y plus y minus z is less than or equal to x minus y plus y minus z. Okay, notice what I did over here. I rewrote this like this. Notice I subtracted a y and added a y. If you simplify this, you just get this. The y's go out. You with me? And now it's just a triangle inequality that we have right here. The absolute value of a number plus a number is less than or equal to the absolute value of the first number plus the absolute value of the second number. The absolute value of a number plus a number is less than or equal to the absolute value of the first number plus the absolute value of the second number. So you see how that comes for free for the absolute value from this. This is the way it's typically shown and proven. So if you were to Google the triangle inequality for real numbers, this is what you would see. You wouldn't see something that looked like this. So that's why I wanted to prove it that way. Okay, and what do you know? Ta-da! Absolute value is in fact a metric on R. Surprise, surprise. That's what we expected. Right? Okay, so now, let's I guess quickly talk about open balls, and we'll take a step back and we'll look at some metrics just to help our intuition.
Real quick, Johnny.
Go ahead.
I don't entirely understand why the absolute value of x plus y isn't just equal to the absolute value of x plus y.
Oh, when is this never equal? Good. So let's look at 5 plus -3. This should be less than or equal to the absolute value of 5
Okay, I already figured
plus.
that. Okay, so I see that now we get the positive 3, and then we're adding to the 5, getting 8. The other one would be 2. Okay, I get it.
There you go. So it can be equal. If the signs are the same, it's going to be equal. If the signs are different, then it's going to be less than. Okay. Anything else? Okay, so now we're going to move on and we're going to talk about open balls again, but this time we're going to talk about them in a more generic way. Up until now, anytime we've been talking about an open ball, we've been using the Euclidean metric for distance. I've been saying it's all the points, an open ball of radius 2 is all the points within 2 of some center point. What do I mean by within 2? We were always using the Euclidean metric. But we can be using any metric. So we're going to be talking about these balls again, but we're going to be talking about them in a more generic way. So up until now, anytime we've been talking about an open ball, we've been talking about a special case of what we're going to mean by an open ball from here on out. So let XZ be a metric space, and for any little x in big X, and for any positive number, epsilon, we define the open ball centered at X with radius epsilon to be the set of all points Y whose distance from Y is less than epsilon. Similarly, we define closed balls to be all the balls centered at X with radius epsilon, or all the points in Y whose distance from X is less than or equal to epsilon. And these are still same intuition that we know and love. It's just now we're going to choose a metric rather than picking a particular metric. So, going to introduce 3 metrics really quick. All these are on R2, just to give us some examples to help us feel good about these things. Okay, so our first metric on R2 is just a Euclidean metric. It's the metric for the distance between 2 points. So I've got a point here P, and I got a point here Q. What's the distance between those 2 points?
Straight line.
It's this line right here, right? So if Q1 has coordinates, or if Q here has coordinates Q1, comma Q2, so that's its X and Y coordinate, and if P here has coordinates P1, comma P2, what is this distance from here to here?
It's Q1 minus Q1 squared plus P2 minus Q2 squared.
All under the radical,
I'm at the square root here.
right? And we get this from the Pythagorean theorem.
Yeah.
Let's remind ourselves, seen a little bit of blank looks, so let's remind ourselves really quick how we get this from the Pythagorean theorem. So we're on some coordinate plane, right? We're thinking about this on some coordinate plane. So this is the point P1, P2. In other words, it's over this way, P1. That's how far over from here it is. Right?
Right.
This point right here is over Q1. Oops. So if we come down right here, this has x coordinate Q1. So what is this distance right here?
Q1 minus Q1.
It's Q1 minus P1. So, gonna erase their coordinates, you know what their coordinates are. Just add some space here. So that's P, that's Q. This distance right here is Q1 minus P1. What's this distance? It's the height of this point minus the height of this point.
Q2 minus P2.
So it's just Q2 minus P2. And what is the Pythagorean theorem? The Pythagorean theorem says that this distance squared plus this distance squared equals this distance squared. So our distance squared is equal to this distance squared, Q1 minus P1 squared, plus this distance squared, Q2 minus P2 squared. Now if I want to know what d is, the actual distance, remember this gives me the distance squared, but I don't want the distance squared, I want the distance. So to get just the distance, take the square root of both sides. And we call that the Euclidean metric.
Does it not matter if it's P1 minus Q1 and P2 minus Q2?
Yeah, because you're squaring it. So flipping the order just makes this, just alternates the difference from being positive or negative. But when you square a positive number, square a negative number, you get the same number. 3 squared is 9, negative 3 squared is 9.
Cool.
So that ends up not mattering. So yeah, order there doesn't matter. Good? And it better be the case, you already helped me with one of our properties. If I'm going to say this is a metric, it has to be symmetric. It better not matter what order. And so hopefully you see intuitively, since those are squared, order doesn't matter. So that's how we know it is symmetric. Let's make sure that it satisfies this property. Notice that we're taking the square root of squared numbers. A number squared is positive, or 0. A number squared is positive, or 0. Adding together two numbers that are positive or 0 gives you a number that's positive or 0. Taking the square root of a number that's positive or 0 gives you positive or 0. So impossible for negatives to come out of this thing. So that satisfies this property. When is it equal to 0? When is this equal to 0? When each of its individual sums are 0. When is this sum 0? When P1 and Q1 are the exact same. When is this sum 0? When P2 and Q2 are the exact same. So the only way that the distance comes out to 0 is if P1 and Q1 have the exact same x-coordinate and the exact same y-coordinate. Or in other words, at the exact same point. So that satisfies that. The triangle inequality in this case is something that we prove in geometry, so we won't do it in this class. But something that you prove in a geometry course is that the distance of either of the legs of a triangle, well, it doesn't have to be a right triangle, but the distance of any two sides of a triangle is always greater than or equal to the distance of the remaining side. Doesn't matter how you draw the triangle. So, we won't prove that. That's from geometry. Anyway, so yeah, this satisfies all the properties. Yay, so it is in fact a metric. Let's come up with another metric. And here's a pretty useful one that you use all the time. Imagine I wanted you to tell me, how far is it for you to walk from here to your house? Assuming you can't cut through any fields or yards or anything like that. Right? If we're right here, and your house is right here, you cannot just go like that to your house. Because there's streets. And so, your path would look something more like this. And so this is called the taxicab metric. Why the taxicab metric? Because it's how taxi cars have to drive in cities. They have to follow this grid. You can't just drive through the buildings. You have to drive around them. And so when we're talking about the distance between 2 points, we're not using the Euclidean metric. If I'm plugging into my GPS system, what's the distance from here to here? It can't just go and calculate the distance and say, this is how far it is. It has to use this taxicab metric. And so what exactly is that metric? Here's what it is. So, our next metric, d sub t for taxicab metric, it takes a point from R2 and a point from R2, point in R2, point in R2, and it spits out a real number, gets you the distance between these 2 points. By doing what? The distance between P and Q is equal to the difference in their x values, take the absolute value, plus the difference in their y values, take the absolute value. So notice that no matter how I draw, notice that here's one potential path you could have taken home, right? Here's another potential path you might have taken home, assuming we're on a perfect grid system. Which of those is faster? The black way or the blue way?
They're the same.
They're identical. In both cases, you went up that much and that much, which is the same as that much. And you went over that much, which is the same as that much. And I could have broken it up into some path like this. And when it's all said and done, as long as you're taking an actual shortest path,
Right, with your stop signs and stuff.
then all those distances add up to exactly that blue, and all those heights add up to exactly that blue. And what is the height of this blue? If this is P, and this is Q, the height of this is P2 minus Q2. If we don't want to have to keep track of order, just put absolute value on it. And this is P1 minus Q1. If we don't want to have to keep track of which order, just put an absolute value on it. Because I could have accidentally called this P and this Q.
It's interesting.
So it's your taxicab metric.
And I guess, you know, I don't know. I imagine in the R2 or R2 plane or whatever, you really don't have verticals ever. It's always
You don't have what?
taxicab metric. Or you don't have diagonals.
I don't know what you mean.
I'm just trying to think of I'm just trying to think how this applies to anything, but anyways, I'm just gonna.
Okay, so it's just an example of another metric. Now let's validate that this is in fact a metric. Again, I'm just going to make it filter your intuition. We're not going to completely rigorously prove it. So first off, is the distance always greater than or equal to 0? Well, we have an absolute value greater than or equal to 0, an absolute value greater than or equal to 0. So yeah, greater than or equal to 0. When is it equal to 0? When both of them are 0. The only way for that to be 0 is if that's equal to that. The only way for that to be 0 is if that's equal to that. We already handled that. So it satisfies the first property. What about this property? If I were to swap my p's and q's, does it change anything? No. We already proved that. It's symmetric because absolute value is already symmetric. And then finally, does it satisfy the triangle inequality? Is this the case? And the answer is yes, because that satisfies the triangle inequality by itself. That satisfies the triangle inequality by itself. Adding those two together still satisfies the triangle inequality. Right? Because we already proved over here that that does. So if a difference in absolute value satisfies the triangle inequality, then a sum of them is going to satisfy the sum of them. Okay. So there we go. Satisfies these three properties. Let's do one more, which is the least intuitive of them. Here's what the metric is. It's kind of like the taxicab metric, but it's called the max metric. You give it 2 points in R2, it spits out the distance between them. How does it calculate the distance? It takes whatever's bigger between the difference in their x values and the difference in their y values. So in this case, this point and this point are the same far away as this point and this point. Because we calculate the x difference and the y difference here. The y is bigger than the x, so their difference is whatever the y is. The distance from this point to this point, we calculate the distance, their difference in the x and y direction. Since the y is bigger than the x, these 2 points are the same far away as these 2 points. However, this point, let me go further so it's just obvious. This point is further away than this point. Because now its distance is however far it is in the x direction, not the y direction. Because the displacement in the x direction is bigger. So it's a weird one. The max metric. Not a very intuitive one. Not as useful a one. Now to really try and establish our intuition for each of these metrics, we're going to draw what an open ball would look like in each of these.
Thank you.
Yep. So with each of these metrics, let's draw a corresponding open ball. Okay, so if this is our metric, so our open ball, when D is our metric, for x epsilon, what does that look like? Looks like, here's our point x. Epsilon is going to be the distance of something like that. It's going to be all the points inside that open ball. All the points whose distance is less than epsilon from x using the Euclidean metric. So it looks something like that. Let's do it for the next case. So if we're using the taxicab metric for x epsilon, what is this going to look like? Trying to draw this one a little bit more precise since it's not as intuitive. It's going to look like where that distance is epsilon. Notice that along the dotted line, it's always the same far away from x. So to get to here from x, you have to go over and down. If you would have just kept coming over, you would have gotten to there.
Right.
So this one, we go over less and down more. So that distance plus that distance is the same as that distance plus that distance is the same as just epsilon. So that's what an open ball looks like with the taxicab metric. Now, what does it look like with the max metric? And I don't know if you were thinking ahead or if you were just calling out a square, but it's going to look like a point at the center of a square. or that's epsilon. These are all these points are the same far away from x. They're exactly epsilon from x. So your open balls could look something like this. Your open balls could look something like this. Your open balls could look something like this.
So is the second and third one not the same?
No. Let me, with the same x and the same epsilon, draw all three balls imposed on top of each other. So you can see their relative sizes. Now, just because it's easier, I'm going to do the circle first. So here's our x. This metric, we can't get as far with an epsilon as we can with this metric. When I try to go epsilon that direction, I can't get clear out here because I can't go straight. I have to go down and up. And I have to waste time going over and up. I can't just go straight out. So if I were to draw this one inside of here, maybe we'll use blue for this one. And then that one would look with the same epsilon. That would look like this. Whereas if we did this one, that one is when we go over epsilon and up epsilon. So it's a square encompassing the whole thing. So that is the exact, given the exact same x and epsilon, that is what your open ball would look like for three different metrics. One metric looks like that rhombus, and one metric looks like the circle, and the other one looks like that square.
What was the M called again?
The max metric.
Max.
Max, because you only take the max of your displacement between x and y. And you might think a metric like that might be useful in determining how long it takes a team to accomplish some set of tasks. If I assign each of you 3 tasks, how long is it going to take? It's going to take as long as it takes the person who takes the longest for you all to finish the task. Right? If I give you the task, put on your shoe, run a mile, how long does it take to finish the whole task? As long as it takes him to run a mile. Unless he's absurdly fast or you guys are absurdly slow.
So these 3 are just some of the...
Just examples of metrics.
Which there could be tons. Like you could do the min.
No.
What?
You can't do the min. Why can't you?
Why?
So then, look at this point and look at this point. They have no change in the x direction, just a change in the y direction.
So it would be 0.
So the min would be 0. But those aren't the same point. And for it to be a metric, it can only spit out 0 if and only if the points are the same.
Right.
So the min doesn't work. Now, I'm sure there's all sorts of crazy metrics we could come up with.
Sure. But that one specifically.
But that one specifically doesn't work. So these are just 3 examples of metrics you can come up with. The same way that there's no, this is a topology you use on this set. There's no, this is a metric you use on this set. A topology is a topology. Pick the topology you want. A metric's a metric. Pick the metric you want. People do this all the time when they're coming up with stats. Talk about, which player is the best in the NFL. They come up with some metric for determining how we're going to measure this. And whatever the metric is, as long as it satisfies these 3 properties, it's a metric. And you can use that to determine who's the best. So, all sorts of metrics out there. 3 examples of metrics on the real numbers. Hopefully establishing your intuition. Any questions on any of this before we switch boards? All right. Okay. Now we're going to do 2 proofs that we already did. But we did these proofs in the special case where our metric was a Euclidean metric. So we always call the same way you have the standard topology on R, R2, or R3, we have the standard metric on R, R2, or R3. And it's the Euclidean metric. It's the standard one, the one that we like to use. So, here's what we're going to prove. Let XD be a metric space if y is in the open ball centered at x with radius epsilon, then there exists some delta such that the ball centered at y with radius delta is a subset of the ball centered at x with radius epsilon. So we already proved this in the case when we were talking about the standard metric. We already proved that if you have some open ball with the Euclidean metric, and you pick some point in there, so here's our x, pick any point in there you want y, we can construct a small enough ball around there, we can pick a small enough radius, we can construct a small enough ball around there such that the smaller ball is entirely within the bigger ball. We did that in the case of the Euclidean metric, now we're going to prove it for metrics in general. And the proof is almost identical. So this may look really familiar. So let y be in some open ball centered at x with radius epsilon. And what's the delta we're going to choose? What's the radius we're going to choose around y? So think about this for a second. Here's my point y. Here's x. Epsilon is this distance. If I'm going to construct a ball around y, how big can the radius be? Huh?
Y to the...
So here's the distance between x and y. Here's epsilon. Distance between x and y, epsilon. What's the biggest distance I can use around y?
subtract
minus
y.
x to y.
Epsilon minus the distance from x to y.
Right.
So take this distance minus this distance, and I'm left with that little distance remaining. Sorry, it's kind of small. Can you all see what I'm saying? So that's exactly what we're going to do. So let y be any point inside the open ball, and let delta be epsilon minus the distance from x to y. So that's the epsilon that we're going to use. So we're going to construct this open ball, and we're going to prove that this open ball is entirely in here. Okay? So how am I going to prove that this ball is inside this ball? I'm going to prove it's a subset of it. So I'm going to pick a random element in the little ball and show it's also in the big ball. Okay, so let z be any element in our little ball. What does it mean for z to be in little ball here? It means its distance from y is less than delta. Right? I need to show that its distance from x is less than epsilon. If I can show its distance from x is less than epsilon, it must be in the big ball. I know it's in the small ball, I need to prove it's in the big ball. Okay, so let z be in the little ball, and observe that the distance from x to z, remember, I'm ultimately going to say this is less than epsilon. So it's in the big ball. That's where we're going big picture. So the distance from x to z, using the triangle inequality, since every metric satisfies the triangle inequality, the distance from x to z has to be less than or equal to the distance from x to y plus the distance from y to z. So, triangle inequality. Now, the distance from y to z, since z is in y's open ball, then the distance from y to z has to be less than delta. If z is in the little ball, it had to be within delta of y. Okay, so then if I replace the distance from y to z with delta, I could have only made my number bigger. I know that this number has to be less than delta. So notice all I do, going from here to here, is I replace that with delta. The distance from x to y stayed the same. So if I replace that with delta, I could have only made my number bigger. I can't make it smaller doing that. Now, what is delta? Delta is epsilon minus the distance from x to y. So going from here to here, just substitute. We have distance from x to y and delta. Distance from x to y cancels out, and we're left with epsilon. So we get this is less than or equal to that, is less than that, is equal to epsilon. Or in other words, this is less than epsilon.
Yeah. Right.
Which is what we're trying to prove.
Yeah.
Pretty straightforward. Second time you've seen that proof. Therefore, z is in the big ball. And so the little ball is a subset of the big ball. Okay. Now, another proof that you've already seen, but just with the Euclidean metric. So let xd be a metric space, then beta equal to the set of all possible open balls you can create is a basis for a topology on X. What was a proof that we did? We proved that if you're talking about the topological space, we proved that if X is R to some power, and D is a Euclidean metric, then the set of open balls is a basis for a topology, and we call that the standard topology. What's the standard topology on R2?
All the unions of
It's the one you get from basis of open balls. That's a special case of this. So this is going to be how we get a topology from a metric. Remember, I told you intuitively, a metric gives us more structure than a topology. It gives us the structure of a topology and then some. So with a metric, we better be able to get a topology. And this is how we do it. We say we're going to let our basis elements be all the open balls. Then use that basis element to generate a topology. And that's the topology. So this is a proof that argues that we can do that. So, given any metric space, let beta be the set of open balls using that metric. That beta is going to be a basis for a topology. Make sense? All right, let's walk through the proof. Pretty easy proof. How do we prove that some collection is a basis? Two properties. Property 1, every element in the set has to show up in at least one basis element. And then 2, you're probably used to the picture. If we have two basis elements with an intersection containing some point, so we have two basis elements, typically we say B1, B2, and they have some element in common. Let's see, what am I going to use for their element in common? Y. Then we can find a third basis element, B3, containing Y, where that third basis element is a subset of these two basis elements. Subset of both of them, or a subset of their intersection. Those are the two properties you need for a basis. So let's prove the first property, that every element in the set shows up in some basis element. Observe that for all little x and big X, X is in the open ball centered at little x with radius 2. Pick a point X, create the open ball with radius 2 around it. Does that contain X? Yeah. Is there anything special about the number 2 there? No. Could have also picked the number 91. Could have also picked the number 0.0001. I just need to show that every little x shows up in some basis element. So for any little x you choose, there's a basis element that contains it. Okay, next. So I'm going to pick two basis elements now, pick something in their intersection, and show a third basis element contains it. So let B1 be the basis element centered at x1 with radius epsilon 1, and B2 be the basis element centered at x2 with radius epsilon 2. Let's just draw the pictures over here a little bit more accurately, just to get a feel for this proof as we go. So we got one ball here. They're not necessarily close to the same in size. Something like that. Here's our x1 with radius epsilon 1. Here's our x2 with radius epsilon 2. So our picture might look something like that. This is B1, this is B2. Okay, so let B1 and B2 be any two basis elements, and let Y be in their intersection. So Y is something in here. There's Y. Okay. By this previous lemma, anytime I have a point in an open ball, there exists some smaller open ball I can create around that point, so that the smaller open ball is entirely in the bigger open ball. You with me? So, I know that there exists some open ball I can create around here with some distance. Call that distance delta 1. Such that this open ball is entirely within this open ball. And similarly, since Y is in this open ball, there exists some distance I can use to construct a ball around here. This time we'll call it delta 2. I'm trying to draw delta 2 just slightly bigger than delta 1. Delta 2, such that that ball is entirely inside this ball. Now really I don't know which was bigger out of delta 1 and delta 2. In this picture, delta 2 happens to be bigger than delta 1. Notice that if I pick the smaller of the two blue balls, it's going to be in both. The big one is only in one of them for sure. The smaller one, notice that the small blue ball has to always be within the bigger blue ball, because they're both centered at the same point. One just has a bigger radius. Right? And so the smaller of the two has to show up in both basis elements. That's what we're going to be seeing here. So, we got basis element B1 centered at x1 with epsilon 1, and basis element B2 centered at x2 with radius epsilon 2, and we let y be a point in their intersection. Then there must exist two numbers, delta 1 and delta 2, such that the ball centered at y with radius delta 1 is a subset of B1, and the ball centered at y with radius delta 2 is a subset of B2. Now let delta equal whatever's smaller out of those two numbers. And observe that then, if I pick the smaller radius, my resulting ball is going to be entirely in B1, and my resulting ball is going to be entirely in B2. Follow that logic?
Yep.
And then, if it's in this ball and it's in this ball, obviously it's in their intersection. So, oh, I don't say that yet. And I say, and also notice that the ball centered at y with radius delta is a basis element. It's an open ball, so it's a basis element. What's my basis? All possible open balls. That is a possible open ball, so it's a basis element. Okay, so then y is in our new basis element, and that basis element is a subset of the intersection of our two initial basis elements. And so beta is in fact a basis. And so we can use beta to generate a topology. Definition. Let xd be a metric space and let beta be a basis of open balls. The topology generated by beta is called the topology induced by D, the metric D, and is referred to as the metric topology. So, if I give you a metric space, you get a metric topology for free. What do you choose as your open sets? Whatever you can get from this basis. It's unions of open balls. And this is how we get the standard topology on the real numbers, or on R2. How do we get the standard topology on R2? We take the standard metric, the Euclidean metric, we create open balls. Any union of open balls gives us open sets. So we've already been doing this in a special case. Now we can do this in general for any metric space. So if you have a metric space, you have a topological space. The converse is not true. Any metric space already has enough structure to talk about proximity. So any metric space has built into it a topological space already. And here's the topological space it has built into it. We call it the metric topology. If you have a metric space, you have a topological space. Okay. Some pretty intuitive proof. So, theorem. U is open in the metric topology on our metric space XD if and only if, for any point in U, we can contain an open ball centered at that point, where the open ball is a subset of U. So, we're just thinking about R2. I want to say, is this shape an open set in R2? Yes, how do you know? Because I can create it from a union of open balls. Or, following what this theorem says, I know it's the case because for any point I pick here, I can create an open ball around that point where my open ball is a subset of the entire set U.
Gotcha.
That's what this is saying. So let's read it one more time. U is open in the metric topology on our metric space XD if and only if, for any point y, this would be my y, for any point y, there exists some delta, some radius I can use, such that the open ball using that radius around y is a subset of U. If I can do that for every single point in U, U is open. And if U is open, I can do that for every single point in U. It's an if and only if. We're going to prove it both ways. So, let's prove the first one. Assume U is open. What does it mean for U to be open in this topology?
It's a union of open balls.
It's a union of basis elements, a union of open balls. So, assume U is open, let y be some point in U. We need to show that there's some open ball centered at y, where that open ball is completely contained in U. So we're starting with this, and we're picking some point in y here. Draw it a little bit further out so we can draw our y. I'm picking some point y. I need to prove that I can create an open ball centered at y, such that my open ball is entirely within U, the whole set. That's what we're trying to do. Okay. Now, since y is in U, and U is a union of open balls, there must have been some open ball containing y that we union together to get U. If U's open, it's a union of open balls. If y's in U, it must have been in at least one of those open balls.
Yeah.
So there must be some open ball, not necessarily centered at y, but some open ball. So maybe an open ball like this, containing y, that's also a subset of U. Now, using this lemma, we know that anytime you have a point in an open ball, you can create a smaller open ball centered at that point. So this lemma tells me, then I can create an open ball centered at y completely inside this ball. But this ball is completely inside U, so my new little ball is completely inside U. That's all the logic is. So then, there must exist some open ball, such that y is in that open ball, and that open ball is a subset of U. So then there must exist some delta, such that the open ball centered at y with delta is a subset of the bigger open ball, which we knew is a subset of U. So we prove one direction. Now the other direction is much more trivial. We need to argue that if our set is such that, so we've got some set U here, and we're wondering, is U open? Here's a property we know about U. Pick any point in there y you want. There's an open ball you can create centered at y, such that the open ball is a subset of U. Pick that point, you can do it. Pick this point, you can do it. Pick this point, you can do it. If you can do that for every point in U, is it the case that U's open?
Yes.
Yes. Union up all those open balls, you get back U. So, assume that for every y in U, there exists some radius such that the ball with that radius centered at y is a subset of U. We can do that for any y in U. Then U is just equal to the union of all those open balls. For each little y in big U, take its open ball. Keep unioning up all those infinitely many open balls, assuming it's an infinite set. And an arbitrary union of open sets is open. So that's open. Okay, there's the if and only if. Okay, so I told you that these open balls are in fact giving us the standard topologies. We use these open balls to create topologies, and that if we're using the standard metric, it gives us the standard topologies. So the Euclidean metric on R2 is what we use to generate the standard topology on R2. The Euclidean metric on R2 is what we use to generate the standard topology on R3. You might think back now to R1. You might say, hold on a second, what about R1? What was our standard topology on R1?
Open intervals.
Any union of open intervals. How do we get that from these open balls? So that's one I'm going to argue still. Hopefully you can see it for R2, R3, R4. But R1, you might be still just a little bit hesitant. Is that really open balls? Is it just open intervals?
Well, couldn't you construct an open interval to have a point at its middle bit point?
Exactly.
Okay.
So going to show a one-to-one correlation really quick. So let D from R cross R by D equal to this absolute value. Then what does our ball look like? The open ball centered at X with radius epsilon. So we're on the real number line. Here's X. And its radius is epsilon. So we're going over to here and over to here. This distance is epsilon. So what is this point right here? It's X plus epsilon. That's epsilon distance that way. What's the coordinate of this point right here? X minus epsilon. Perfect. So the open ball centered at X with radius epsilon is the same thing as the open interval X minus epsilon to X plus epsilon. So that's all we're saying here. Or you could always go from the reverse. Go the other way. Say I gave you an arbitrary interval AB. So if I instead said, let's look at the interval from A to B. This is A, this is B. Now convert that to an open ball. Well, what's the center point of those two numbers? What's the middle of 10 and 30? 20. You just take your average.
Oh,
Right?
yep.
So add together, divide by 2. So this middle point is just A plus B divided by 2. And then what's this distance? It's half the total distance. What's the total distance?
Between A and B plus B? B minus A.
B minus A. So what's the radius?
B minus A divided by 2.
B minus A over 2. So your x is B plus A over 2, and your epsilon is B minus A over 2. So AB is the same thing as the open ball, B plus A over 2, comma, B minus A over 2. Right, as an open ball.
Yeah. Yep.
So these are just open balls. One more thing I probably should have said. I said that this is the standard metric on R. Wait a second. Aren't we always using the Euclidean metric? So the Euclidean metric on just R should be the square root of x2 minus x1 squared. Well, it turns out that that's just another way of writing the absolute value of x2 minus x1. Same thing.
Well, yeah.
And you can think through that yourself. Not hard to.
It's not hard to figure out.
Okay. Right? Square always makes it positive, and then the square root one doesn't. So you're just always making your result positive. Always making your result positive.
Yeah.
Always making your result positive doesn't mean always get rid of the negative sign. Two different things. Sometimes the negative sign is what makes your result positive.
Sounds like a combination.
Yeah. Okay. So it is the standard metric on R1. It is using the Euclidean metric. Absolute value, just a special case of the Euclidean metric on R1. Okay. Now just for some weird examples that we define metrics on. Standard topology on R is the Euclidean metric. We already said that. Okay. I know you guys haven't had calculus yet, so you need to just throw some fancy symbols at you that you can start drawing and start looking smart. This is just to give you an example of something that it might seem very unintuitive that we can talk about a metric on that thing, and yet we can't. Okay, so the symbol I've got to introduce to you is this integral symbol. Here's what it means. So here's some function f of x, right? And a is some point and b is some point on your x-coordinate axis. So the area under the curve from a to b is going to be some number. That's what we mean by the integral. The integral from a to b of f of x, with respect to x is how you read that. You don't need to worry too much about that dx right now, but the integral from a to b of f of x with respect to x means the area under the curve f of x from a to b when we're going in the x direction. So we weren't doing a to b in the y direction. That's one way you can think about it. Okay. That's all that is. Fancy way of talking about area. Okay? Alright. So now, and intuitively in R2, what's a continuous function?
Something that you don't have to pick your.
You don't pick up your pencil. If you can draw from A to B without picking up your pencil, it's a continuous function on AB. So now, let C, close bracket AB, be the set of all continuous functions f from AB to R. What does that mean? It seems dense, but when I draw it out for you, you're going to say, oh, that's all it is. So here's A, here's B. Follows up. I need to draw a continuous function that has AB as its domain. Right? So I have to start at A, and I have to keep drawing until I get to B without picking up my pencil and make sure it's a function. Here's one example of a continuous function from A to B. Here's another example. Here's another example. Here's not an example. Tell me why the one I'm about to draw is bad. I'm drawing blue. Here's not an example.
It's not a function.
It's not a function. One input is going to multiple outputs, not a function.
Right.
So this is shorthand for all the continuous functions you can draw from A to B. It's an infinite set, infinite number of functions. You with me?
Yep.
We're going to define a metric on that set. It's called a function space.
Okay.
Seems pretty crazy, but it's a very normal thing to do. It's one of the huge leaps you gotta get students to take in mathematics is get comfortable thinking about functions as elements of sets. It's a huge leap to just get comfortable with your brain thinking that way. But that's how we're thinking about it. So here's our set. Our set is a set of functions. Who cares? It's a set. Infinite number. What's our metric going to be? So this is a set of all continuous functions f from a, b to r. Let f and g be any two functions in there. So clean up my picture again really quick. f might be something like this, and g might be something like this. I want to come up a metric on this. I want to come up with a metric that gives me the distance between these two things.
Okay.
You with me? Okay. So, what would be a very natural metric, just using your own words, what would be a very natural way to talk about the distance between the black line and the blue line?
You take every point in the black line and find the distance to every point in the line. Or
In regards to the x.
And add them all up?
you look at the x point. So you take x, you take f of x and g of x, and then you compare their distance on the y-axis.
So their distance right here is between them is 0. The distance between them right here is, I don't know, 10. The distance between them right here is 5. Or should we say the distance between those two lines is?
Would you like to do an average or something?
Yeah. Well, that doesn't work really.
The average distance between them?
I don't know. Is that, I don't know how many
It's not
other
very useful.
way to answer
I
that.
mean, it's not useful.
Yeah, probably isn't, but.
One way to think about it. No. It's a perfectly valid way to think about it. I think that would work as a metric. Whatever our metric is, we want to make sure that this function and this function have a distance between them of 0, because that's the same function,
Well, yeah,
right?
it would do that. Yeah.
So the metric that we have written out here is we're just going to calculate the area between them. So we're just going to calculate, maybe grab orange really quick, make sure it's clear what we're talking about.
Well, yeah, that checks out.
We're just going to calculate this area between them and call that the distance.
I guess that makes sense.
Which, if you took their average distance and you multiplied it by the width, would have given you the same thing.
Awesome.
So you were that far off from even where we were naturally going. Anyways, so there you go, and that would give you the distance between them. So that's what this is saying. We define the distance between f and g to be the area of the function f of x minus g of x. Take its absolute value. So what does the function f of x minus g of x look like? Which one did we say was f? Was it blue?
Did you label it wrong?
I just said when I wrote it. I can't remember what I said. So we'll pretend that that's f and that's g. You with me?
Yep.
F of x minus g of x, let's plot that function really quick. We're going to probably have to scale down because we're running out of space. So f minus g, should have done this more centered. So right now we're doing f minus g. So that's like a 2, I don't know, that's like a 6. 2 minus 6 is going to be like -4 down here. And then the distance, f minus g, it gets closer and closer and closer to 0, right? And then f minus g starts coming up here, reaches its highest point somewhere around here, and then curves back down a little bit. Something like that. Not terribly to scale, right?
Works.
So here's f minus g. If I would have taken its absolute value, that just flips this portion back up here. So that just flips this up here instead of down there. So I get rid of that and flips up there. You see that? And then when we take its integral, that just calculates this area, which it turns out would have been the exact same thing as just the orange there. My picture's blank a lot. Don't put too much stress on my picture. Because the height, if you think about a little rectangle right here, this little rectangle would have the exact same area as the exact same little rectangle right here. They have the exact same height because it's f minus g. F minus g. Anyway, so there you go. And that is defining a metric space on a set of functions. Seems pretty abstract, but it's actually an extremely useful thing to do.
Yeah.
Do it all the time.
Pretty cool.
Shoot. Kind of cutting it for time. I don't know how interested you would be in it. I was going to go a little bit into a metric that we use for information in like computers, and then a metric that we use in like DNA. I don't know.
I
Not that interested in those types of applications. Rather just keep going.
Yeah, I'm very interested.
Maybe you can just briefly talk about them and not do a deep dive. So we have a difference in binary strings. When we want to talk about the distance between two binary strings, it's pretty straightforward. So if I have 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 1, and I have another string 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 0, 1, and I want to talk about the distance between those two things, it's pretty simple. I just sum up the places where they're different from each other. So same, 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 different, different, same, different, same, 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 same. So these differ by 3. Error correcting, that might be going on too much of a tangent.
Oh yeah,
I'm familiar with it.
I watched a video about that.
Error correcting, so when you're sending data, that you care about it being correct, sometimes you don't care if data is correct, and if a 1 turns into 0, a 0 turns into 1. That would be like when you're watching a movie or listening to some audio. You know, if you're watching a movie and a pixel gets lost in transmission, you don't care. You don't want to pause your whole movie to make sure you got the correct pixel value showing up. So you don't care. But there's times where you very much do care about the data that comes up. And so we pretty much just use this basic metric for figuring it out, but we have special code words that we use when we send data where we care about what the data is. So we use special code words. I'm going to write 2 stupid code words just to give you an idea. So one code word will be 0, 0, 0, 1, 1, 1. And another code word will be 0, 0, 0, 1, 1, 1. Notice that this code word and this code word differ from each other by 6. They have a difference of 6 between them. Now we wouldn't just have 2 code words, we'd have a bunch of code words I could use to send data with. What's the difference between these two? Let's use one that just has a difference of 4, maybe.
How are those different?
Oh, I meant to draw in reverse order. Thank you. I meant to write 0, 0, 1.
Wait, look.
Okay, sorry. I gotta figure out why you give me such a weird look. It's like, 6 is too much? Let's go to 4. Okay, so here's 2 potential code words. I could have a whole list of code words. The trick is when I come up with my code words, make sure that they have enough of a difference between them. So these 2 differ by each other by 4. I create longer code words and then create a bunch of them that the closest they are is within 4 of each other. Works better when it's an odd number, 5, but you'll get the idea. Now, when some message gets sent to me over the wire, and let's say that the message I got is 111011, what's its distance from this one? 1. What's its distance from this one? 3. 3. And so in error correcting, we say, oh, you meant to send this one. So since we look at the code words that we do, we say, oh, that should have been a 0. And that's how we error correct on the back end as this data comes in when you care. If we got one where the difference was too big that we couldn't determine should it have been this one or this one or this one or that one, then we have to re-request it. So that's why it can be much slower when you care about the data coming being actually accurate and you didn't lose any information. And so you can imagine with bigger code words, obviously these are stupid small, with bigger code words and more combinations, then you can be pretty confident that the word that you got that had an error had to be this one. Because the odds of there being 1 mistake in it might be, I don't know, 1 in 1,000. The odds of there being 2 mistakes in it then are now 1 in a million. The odds of there being 3 mistakes in it now are 1 in a billion. And so if you make sure that you have a difference where it can have up to 3 places screwed up and we can always figure out what it was, but more than that, we'll just re-request whatever it was. Or whatever. So that's a fastest I can cover error correcting codes for that. For genetic information, when we talk about nucleotides, similar idea. But with genetic information, we can't control the number of bits that we send like we can when I'm sending you an electric signal. I can make it very clear how many I'm sending. It's just all that will get confused is without a 1 or a 0. With genetic code, imagine that you had some series of nucleotides, G, A, C, C, T, T, A, and then we could use the same metric that you might already think. We could use a metric that G, A, G, C, T, T, A. You might think, okay, those two sequences of nucleotides only differ in one place, right? But now, imagine, so we call that a difference of 1, and that is in fact what we do. But now imagine instead that over here I wrote G, A, C, C, T, T, A.
We reread the wrong one twice or what?
Well, now we're talking about genetic information, so somehow another anodyne got hooked in there. And so how close are these to each other?
Like 6, I think, away.
So if you just do the way that you're used to, you say those are the same, 1, those are the same, 2, those are the same, 3. Right?
Well, what about the one Patrick A on the top? Where there's
Oh, and maybe 4. Maybe. I don't know. Coming up with the metric for it. So what they do is they say how many deletions or insertions or replacements would you have to do to make this one look like this one or this one look like this one. And in this case, it's only one deletion. If I just delete that, they're the same. So the metric they use says that these two are 1 apart. Because one deletion, yeah. So it takes more processing to determine how close are they, because you have to try out these combinations, and there's going to be tricks for trying it out.
That makes more sense.
But yeah, the possible ways to measure is going to go out in a tree, and you're going to have to search the tree.
Yeah, you actually have to have a limit on how far you insert.
Yeah, there's going to be natural bounds that it's not going to go over n squared or whatever it's going to be for your algorithm. And so, you know, if I checked n squared and then go find the min value that came out or whatever. And so that's how they do it for genetic material, just looking at nucleotides. Should we take just one more second to do just a little bit more of a detour to that? Because this genetic material, even then, that doesn't give you the full picture. Because if I give you some series of nucleotides, G, A, T, T, A, if I give you that series of nucleotides, if we were to get down and look at the actual chemistry of it, this doesn't guarantee you how the actual chemical bonds between those molecules is going. And there's multiple ways that we could get these same series of nucleotides like this, that you would represent this way, but maybe in one way the structure comes out with keeps looking like this, I don't know, and another way it comes out looking like this. I don't know.
DNA strand?
Not necessarily DNA, just some series of nucleotides.
Oh.
So we're talking more general than a full, remember DNA, you've got the whole helix structure, and you've got them bonded to each other across it. So we're talking about just some series of nucleotides. So we're talking about genetic information in general rather than human DNA or animal DNA or whatever.
Okay.
And so for the same exact nucleotides, they can actually bond together in slightly different ways, even maintaining that order. And so, people often talk about how much information could you capture in these nucleotides. It's not just the order of the letters that you can capture information in. It's also in how they're bonded to each other, which they call the topological structure of the genetic material in question, of the nucleotides. And then even on top of that, when you start talking about like DNA strands, it also matters how they're wound up, how the strands themselves are wound up. And so some information can be captured or lost even in that kind of structure. So a lot of information that can be captured in this genetic material, and it's not as simple as just reading the nucleotides.
That's insane. I didn't know that. I've always thought it was just the, what you call it?
Nucleotides?
Nucleotides, yeah, I didn't know that.
Well, that's a metric that they can use. You can't sit there and do an analysis on, now how is this thing twisted up? And so knot theory, which started out seeming like this super niche field of mathematics with just the least applications you could possibly think of, is now a very active area of research for microbiology and doing an analysis of the way that proteins and chromosomes knot themselves back up.
Yes.
One of the current theories as to what leads to aging, so you listen to it, they find these 3 basic properties that they think contribute the most to aging. One of the ones that they think contributes drastically to how fast you age is your body rewinding up the chromosomes after your cells split incorrectly. And so some information is lost because it gets wound up wrong. Supposedly one of the factors now. Or at least a few years ago, last time I bothered looking into it. So, a lot of information there. Anyways, those are 2 quick tangents. When we come back, we'll be talking about properties of metric spaces, and then, well, we'll see where we go from there.
Okay, thank you.
Yep.
Did you ever consider switching